Hello, this is Mr. Hopkins Maths, and this is our last binomial distribution video. We're looking at real life problems in this. We're going to take everything we've done in the last three videos, which along with this video are a playlist on the channel as the binomial distribution playlist. And then what we're going to do is, with everything we've learned, we're going to apply it to some real life problems. Remember to like this video if you found it helpful, and subscribe so you know when the next videos are coming out. We're looking at doing some hypothesis testing soon as well. So this first question says, a market researcher is interviewing people in a busy city centre. Now, we're going to assume that the probability of each person they approach agreeing to an interview is 0.3 and that each person can be considered an independent trial. Now, during one session, they approach 30 people. First of all, we're going to look at suggesting a suitable model to describe the number of people, X, who agree to an interview. And then we're going to look at the remaining sections on there as well. But we're going to take each one in turn. So that's what we're looking at. We're going to look at part A first of all. Now, to suggest a suitable model to describe the number of people, X, who agree to an interview, we're going to have a look at seeing if it meets binomial first of all. Because if it doesn't meet binomial, it could be another distribution, just one that we've not looked at yet. And if you are in year 12, doing A-level maths, it's probably going to be binomial. But this is how we're going to look at it. So there's a fixed number of trials. We approach 30 people. Now, as you can see, I'm listing the situation and the context as well. And you might want to put that into a form of a sentence when you're doing it yourself. All the trials are independent as per the question. And we see that here is that each person can be considered an independent trial. Okay. There are two possible results. They agree to an interview and do not agree to an interview. There's a constant probability of success of 0.3, and that's stated in the question that the probability here is 0.3, and we're assuming that's the same for everyone. You can see in the question the word assume. And that X is the total number of people agreeing to an interview. Now this is us defining our random variable X essentially right there. So what we would say is that all the conditions for a binomial distribution have been met. And we must state that. Have been met. So all the conditions for a binomial distribution have been met. And then the last thing for us to do is to state it. X is distributed binomially 30, 0.3. Now normally we'd say let the random variable X be the number of people agreeing to an interview, but as part of our conditions we've actually listed that there. We said X is the total number of people agreeing to an interview. So we stated that. And we pulled that from the question there. So that's us. We've done part A. We've looked at a situation and been able to state whether it's binomial. So that was back in video 1 of this section. Find the probability that more than 10 people agree to an interview. So we're just going to use either tables or your calculator. And if you want to find out how to do that, you can look at video 2 in the playlist. So that takes you through how to find out this type of thing. So what we want to do is we want the probability that X is greater than 10. So more than 10 people. And remember, your tables are calculated when you look at cumulative binomial distribution, will give you that or less. So in our case, we're looking at, say, 8, 9, 10, 11, 12, so on. We want that, so we're going to have to get rid of all of this stuff here. So 0 up to 10. So we know that all probabilities add to 1, so it's going to be 1 minus the probability that X is less than or equal to 10. Because we want 11, 12, 13 and so on. Now, using your calculator or table, you would find that value as 0.7304. And a quick calculation will tell you that that's 0.2696. the probability of us getting more than 10 people agreeing to an interview is 0.2696. So you've got about just under a 27% chance of that happening. So let's have a look at the next part of the question there. So the next part says, find the expected number of people who will agree to an interview and the variance of x. So the expected number, which is E brackets x, is how we'd write that. So that's the number of trials times the probability, which is very simply just 30 times 0.3, and that's going to give us a value of 9. So the researcher should expect 9 people to agree to an interview, and you could probably write that. So researcher could expect 9 people to agree to an interview, just as a statement or a sentence there. And then if you want to find the variance, so the variance, that's n times p times 1 minus p. And so that comes out as 30 times 0.3, and that will be times 1 minus 0.3, which is 0.7. And if you plug that into your calculator, you'll get an answer coming out of 6.3. Okay, so our expected number of people is 9 and our variance is 6.3. So then let's look at the next bit. The researcher counts those agreeing to an interview in 100 samples of 30. So they've done 100 batches of 30 people. They find that the mean number of people is 8.9 and the variance is 3.2. Comment on the assumptions that the probability of a person agreeing to an interview is 0.3 and that each person can be considered an independent trial. So these are two parts of a question. So we want to comment on the probability and the independence. So that's two things. So we approach each bit separately. So the first thing we're going to do is we're going to look at the probability. So the observed mean is approximately the same as the mean predicted by the model. So the observed mean that we've got here is 8.9 and we predicted a mean of 9. So the assumption that the probability of a person agreeing to be interviewed is 0.3 does seem justified. And you can look at that through the mean value there. Now, the next thing we want to do is look at the independence. So if we have a look at the independence here, so this is going to be us comparing our variance, the observed variance is very different. Now we've got an observed variance here of 3.2, but our variance that we calculated was 6.3, which is very different value. So it's completely different from what we worked out theoretically. So this suggests that at least one of the conditions for a binomial distribution is not satisfied. And the only real possibility left, we've got two outcomes, agree to an interview or not agree to an interview. We've got a probability that's 0.3 and our probability we've calculated seems justified. We have a fixed number of trials. We're approaching 30 people each time. So the only thing left is the independence. So the assumption that each person can be considered an independent trial is probably unlikely to be valid. So that question brings together everything we've done so far. It looks at, is it binomial? It looks at the cumulative binomial. It looks at the expected or the mean and the variance. And then it all brings it together in a way that stats questions normally tend to have, which is, can you justify this? Comment on this. And so that final step of being able to look at everything you've done and make a comment on that is normally a key part of this. So let's have a look at another question. A student has to take a 50-question multiple choice exam. Each question has 5 possible answers of which only one is correct, and the student believes he can pass the exam by guessing answers at random. So the first thing that we're going to have a look at is A. How many questions could the student be expected to guess correctly? So first of all, we want to define a random variable first to see how it's going to be distributed. So we're going to let the random variable x be the number of correct guesses in 50 questions. Then we have to say how it's going to be distributed. So x is distributed binomially. So there's 50 questions. And because there's 5 questions, we can infer that with one being correct, our probability is 0.2. Then we can use the formula for the mean or expected value, which is EX equals NP. So that's just 50 times 0.2. And we're going to get an answer of 10 questions. So a student that guesses at random could expect to guess about 10 questions correct. If the pass mark is 15, what is the probability that the student will pass the exam? So we already know that X is distributed binomially, 50 questions, 0.2. So for the student to pass, if the pass mark is 15, we want 15 or more questions. So if we're thinking about this is the number of questions correct, we want 15 or more. So what we're going to be discounting is we want to discount 0 all the way up to 14 questions. So what we want is the probability that X is greater than or equal to 15. But in order to do that, the table will give us that or less, so we do the probability of 14 or less, and we take that away from 1. Now, looking at tables or your calculator, that's going to be the chance of you getting 14 or less answers is 0.9393, and that works out as 0.0607 to 4 decimal places. So the actual chance that a student will pass the exam is just a little over 6%. So they've got quite a low probability of passing there. The examiner decides to set the pass mark so that it is at least 3 standard deviations above the expected number of correct guesses. What should the minimum mark be? Well, we need to work out what the standard deviation is first of all. So if we look at this, if we look at the variance, that is NP 1 minus P, and that's going to give us 50 times 0.2 times 0.8, and that works out as a variance of 8. So we know that the standard deviation is the square root of 8. So, but what is the question actually asking here? Well, it's asking us to set a pass mark so it's at least 3 standard deviations above the expected number of correct guesses. So essentially what we want to do is the expected number of correct guesses was 10, and we want to do 3 standard deviations. So we want to add on 3 lots of root 8, which is essentially 10 plus 3 lots of root 8. And if you plug that into your calculator, you will get an answer of 18.485 and some stuff. So because the value that it has to be set at is more than 18, so it's between 18 and 19, it's more than 18, so it can't be set at 18. We then have to round up, although it doesn't look like it's going to round up, we have to round this up to create a pass mark of 19. So the pass mark is 19. So remember, always think about the question in context. What is it actually asking you to do? Don't just round off just because it looks right. Think about it in the context of the question. It's like the old questions in exams of, if I need 4.3 coaches, I'm just going to send 4 coaches off. But those children that need 0.3 of a coach to go on their school trip now don't have a coach. So you always need to think about context, and sometimes you're rounding up where a number would show that you'd normally round down. So this is a different question which is going to involve us creating 2 variables now. The probability of a banana bought from a supermarket being brown at time of purchase is 0.15. And it is a scandal that there are so many bananas that are brown at time of purchase. We want to find the probability that in a random sample of 30 bananas, there are more than 2 bananas that have gone brown. Let's define the variable first of all. So let the random variable x be the number of bananas that have gone brown. And then we know that x will be distributed binomially. And then we've got 30 bananas in our sample, and our probability is 0.15. And we're looking to work out more than 2 bananas. So P of x, so we've got 0, 1, 2, 3, 4, 5, so on bananas. We want more than 2, so we're going to be getting rid of 0, 1, 2, 3. So more than 2 is the same as 1 minus probability of x being less than or equal to 2. And again, we can just work this out using tables or a calculator. Again, if you want to know how to do that, video 2 in this series, part 2, which is cumulative binomial distribution, will give you that information. But if you do find that out, it is 0.1514. And then that gives us an answer that the chance of finding more than 2 brown bananas in my sample is 0.8486. Now, part B says that bananas can be bought in boxes of 30. Now, Archie buys 3 crates, or 3 boxes. I should probably say boxes. Not sure why it says crates. But in a supermarket, they're probably very similar things. So we want to find the probability that more than one box contains more than 2 bananas that have gone brown. Now, in this case, we need a new random variable. So let's define that first of all. So we're going to let the random variable y be the number of boxes that contain more than 2 brown bananas. So we're going to define y is distributed binomially. Now we've got 3 boxes that Archie is buying, and the probability of a box having more than 2 brown bananas, well, that's what we've worked out in part A. So the probability of that happening is 0.8486. So let's just grab a new page. So we know that y is distributed binomially with 3 boxes and a probability of 0.8486. So the question asks us, find the probability that more than one box. So we want the probability that y is greater than 1. So if we've got 0, 1, 2, 3 boxes, more than 1 are these ones, so we want to get rid of 0 and 1. So it's 1 minus the probability that y is less than or equal to 1. And remember, we're dealing with the random variable y, not x, so everything should have y in there at this point. Now, going from a table, plugging that in is a bit difficult because we don't tend to have that. So you've got a couple of options here. You can either work out using by hand, using the formula which you can find in lesson 1, which if you do that, the probability that y being less than or equal to 1 equals the probability that y equals 0 plus the probability that y equals 1. And you can work those out using a formula and go from there. However, if you're using one of the more modern calculators, you can plug in your value. And doing that, we get 0.0618 and some stuff. And just keeping that to 4 decimal places, that gives an answer of 0.9382. So in his purchase of 3 boxes, he's got more than one box that's got more than 2 brown bananas, is 0.9382. Let's have a look at our last example. A teacher sets our class a multiple choice test. In this test, there are 20 questions and each question has 5 possible answers. The teacher wants to make it very unlikely that a student who guesses the answer to every question would pass the test. How high should the pass mark be to give a student guessing the answer to every question less than 10% probability? What we know is that there are 5 possible answers. One of them is correct, so we know that p is going to be 0.2. We can then define our random variable. We're going to let the random variable x be the overall score of a student that always guesses. So then we can define that as x is distributed binomially. There are 20 questions and a probability of 0.2. Now, we want a pass mark. So a value that's equal to or greater, so we want the probability that x is greater than our minimum pass mark, so our minimum, I'll just use lowercase m for that, and that has got to be less than a probability of 0.1. Now that means that I want the probability of x being less than my pass mark to be greater than 0.9 or 90%. How do I do that? You can either look up the tables and find out which value switches over to 90% and then go one above that, or what we can do is we can use our calculators. Now this is an option which we haven't gone over yet in our calculators. So we're going to pull up our electronic class whiz. The mode which we're going to go into is we will select our menu and go into option 7 as normal. And then we're going to go down to binomial cumulative distribution, which is option 1. But the difference here is that instead of going into variable, we're going to go into list. Now, under X, which you see here, we're going to select, just enter some values. So what we might do is we might, since there's 20 questions, it's probably going to be a fairly low value. So we'll enter 0, and then you want to press your equals key. And then let's stick in a few values, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we'll do that. If you don't then enter anything and you press equals, it'll give you a chance to put in the values. So we are dealing with a distribution of 20 questions with a probability of 0.2. And when I press enter and insert that, it's going to take a moment, but then it's going to give us the cumulative binomial distribution for that or less. So this one here at the top, the probability of getting 0 or less is 0.0115. Getting 1 or less is 0.0697. Now we wanted the point where it went above 90. So you want to just scroll down. And as you can see here, 5 is about 0.8. And then 6 is where it goes to 0.9133. Okay. Now we wanted that less than that to be greater than 90%. So my pass mark, because we want is 6 is our 0.9133, so we worked out that the probability x is less than or equal to 6 equals 0.9133. We wanted this situation here though. Now, in order to make that into just a less than, the probability that x is less than 7 equals 0.9133. Those mean the same thing, less than or equal to 6, but less than 7. So our pass mark equals 7. So in order to pass this is 7. So then the probability that a student who always guesses will pass the test is less than 10%. So that's our work on binomial distribution done. We're going to be looking at hypothesis testing coming up soon. So if that's something you're interested in, remember to subscribe and you'll know exactly when that video is released. Remember to like this video if you found it useful, and I will see you next time.